Okay, happy day and welcome. We are talking titration curves today. Okay, so we know we've talked about titrations before. And in my mind, I think the best thing to do is always to kind of like take a look to see what a titration looks like. Like what's the equipment that's used in a titration? And then that always helps me to get an idea of like, what are we actually doing in a titration, okay? So what do you think we're doing in a titration? We're probably going to be doing what? Neutralizing something, probably to try to figure out what? The molarity of something, the molarity of an acid when you know the base. That's usually what a titration is going to be very useful for, okay? So a lot of times what they'll do is they'll put a base inside of a burette, and then what is this thing called down here? Erlenmeyer flask, the Erlenmeyer flask. You can add an acid into the Erlenmeyer flask, and then usually you also add what into the Erlenmeyer flask? Not only the acid, but starts with an I, an indicator. Because, very good, you're going to need to see what color it changes to, okay? And so what you could do is, in this case, they're giving us the option of like, do we want to select, use a strong acid or a strong base, or do we want to use a weak acid or a weak base? And so let me just kind of fast forward. They're filling everything in, and so you can select which acid you want, which base you want. What's going to end up happening is they're going to start titrating, and they're going to start dropping it in, and eventually they're going to get to a point where it turns pink, okay? They went way too fast that time. They really should have been drop-wise. And so then what you can do is you can go ahead and you can calculate your base simply by doing this. Let me just pause the way this video is here. You know the molarity of your acid, and you know the volume of your acid. That hasn't changed. It was 25 mils. So people will say, okay, but remember how we said M1 V1 over V2 to find your new molarity? You're not doing that because you're using Ma Va equals Mervet. That's the equation of what you're going to use. So you're going to use Ma and your Va, and then for our volume of our base, that's how much you dropped. So depending how much base you dropped in, that's going to be your VB, which means all that's left is to calculate your MB, okay? It's a basic idea of doing an acid-base titration, okay? Once you're done with that, then what happens is you can actually create a curve, okay? So once you're done with your titration, you can create a curve. This is a very standard titration curve. If you have anybody want to guess what was inside of our flask if it's down at 1? Strong acid, and we're titrating it, and eventually we're going to end up with something that is a pH higher than 12, which means we're going to probably end up with what? A strong base. Now, why did this happen? If you stopped right at the point where it was neutralized, anybody want to tell me what volume that would be? Where was it neutralized? At exactly 50 mils. If you stopped right at 50 mils, that's where it's neutralized. What they did was they actually passed the neutralization point in order to get a curve like this. So you start off with your strong acid, and I'm going to end up showing you in the video too what happens when you have a buffered solution. The curve is going to change a tiny bit when it's something that's going to be a buffer, and you'll be able to tell how that ends up changing. So this is very standard. This is, you're titrating a strong acid with a strong base. Where's our equivalence point? At 7. When your pH is 7, which is what we expect, if you have a strong acid with a strong base, you're going to expect your pH to be equal to 7, okay? Just to kind of give you a little bit of, just to kind of see what some of these titration curves look like, then we can come back into the notes here. You can see this line is outlining in black what our strong acid, strong base line would be, okay? What do you think is happening here? If our pH is starting closer to like a 3, that might be more something like what? A weak acid. And what happens is when you have a buffer, your line's going to be a little bit different. And then what we're ending too is it looks like we're still ending at around a 12 or something like that, which means our base is probably strong. So where's our equivalence point now? It's around a pH of what? Closer to what? Closer to 9, not 7. So if you have a strong base titrated with a weak acid, you're going to expect your pH to be a little bit higher. Obviously, if you have a strong acid with a weak base, you're going to expect your pH to be where at the equivalence point? a little bit lower than 7, okay? All right, so let's go back and let's just go right through the notes. Okay, so let's go back to what is a titration. Okay, so we see here it's a procedure for carrying out a chemical reaction between two solutions, adding one from a burette, and that's what they typically will call the titrant, into the other one, allowing measurements to be made. And so it says for a reaction between an acid and a base, a titration is useful for measuring pH at various points, or what we could do is we could figure out what, using MAVA equals Mervet, what is the concentration of a particular acid or base when we know the concentration of another one. So let's say you accidentally forgot to mark the concentration of something, and you have a container of HCl, and you want to know what is the concentration of it, or it's been sitting in a cabinet for a while. What's the concentration of it? This would be a good way of figuring it out, is using a titration. Okay, so calculating the pH during a titration. So this is a very popular question. They'll say that you're in the middle of a titration, not necessarily asking you what it is at the equivalence point, but just at a random point. So since this means that you stopped mid-titration, how do you calculate the pH when you're not at the equivalence point? Okay, so what is the equivalence point? Let's make sure that we know that first. So it's the point at which exactly enough titrant has been added to react with all of the substance being titrated, and there's no titrant left over, okay? So that's going to be our equivalence point. So when you're at that point, what we say is, we say that the moles of the acid and the base are simply going to be equal to each other. So as long as they are equal to each other, then that's our equivalence point. And according to the stoichiometry, so remember we have to take a look at our stoichiometry. So in an acid base, typically we're used to seeing a 1-to-1 ratio. So the equivalence point is going to be the point where your moles are equal to the moles of the substance initially in the solution. So it says, notice that the pH is going to increase slowly at first, but then once you reach that point where your equivalence point is, it's literally within like 1 milliliter that it jumps. Here we can see that it's jumping from about a pH of about 1, jumping to a pH of about 12, just within a couple of milliliters of each other, okay? So this says calculate the pH during a titration. We've got 4 steps. We've done this before. So remember, step 1 is use your MAVA equals Mervet to figure out your moles. Step 2 is find your excess amount. So we're going to use MAVA equals Mervet. Then we're going to find our excess. How are we going to do that? By subtracting our 2 mole amounts. Step 3 is we're going to find our new molarity. Remember, the way that you do that is you simply take your moles, you divide by your new liters though. So this is going to be important that we're actually doing moles divided by of the excess divided by our total liters. So you're going to have to add up your 2 volumes after you've mixed them. And then the last step is once you know whether it's the H plus or the OH minus that was in excess, once you know which one it was, you're simply going to negative log it. So if it's your H plus, that's going to give you your pH, or you negative log your OH minus. Okay, so let's take a look at these problems. The first one says, what is the pH of a titration if I'm titrating 50 mils of the same molarity of both a strong acid and a strong base? Well, that's pretty easy. If you go to do MAVA equals Mervet, you're going to see that it's exactly the same. 50 times 0.2 and 50 times 0.2, you're going to get the exact same answer, which means the moles of my acid are equal to the moles of my base. Therefore, and if it's a strong acid, strong base, which it is, my pH should be equal to 7. Now let's give it 3 sig figs since I've got 3 sig figs on my molarities. Okay. Now let's see what happens if it's a random point in the titration. Again, we've done these already, so let's see how we do here. Step number 1. Step number 1, we said we're going to do our MAVA equals Mervet. So let's fill this in. I've got 50 mils of a 0.1 HCl and 49 mils of a 0.1 NaOH. Okay, I want you to guess first. So where do you think the pH is going to be? We're only 1 milliliter off from being neutralized. We know if we have 50 and 50, we're neutralized. Do you think the pH should be more acidic or more basic? It should be pretty obvious to you, okay? So let's see if you are right. Let's figure out the actual pH of what it should be. So I'm going to fill in my values. I've got a 0.100 molar HCl, and I have 50 mils. I'm going to switch this to liters, so 1, 2, 3 loops back. So I'm getting a 0.0500 liter there. The molarity of my base is the same, 0.100 molar. I'm going to multiply that by, again, shift my decimal 1, 2, 3 loops back, 0.0490 liters there. Okay, this is a good time to go over calculating without a calculator. Okay, so remember, If it's numerator to numerator, you're going to go in the opposite direction, or numerator to answer, you're going to go in the opposite direction. So make it easy to calculate and then shift your decimal. If it's numerator to denominator or denominator to answer, you're going to go in the same direction to cancel those out. So pretty easy. So let's do, I've got a 0.100 times a 0.05. And I don't really care about the zeros, but I'm just going to simply make this 1 times 0.05 because I know what that is. And 1 times 0.05 is simply 0.05. And so what I'm going to do, though, is you can either shift it right now or you can shift it in your answer. It doesn't really matter. So I know that it's equal to 0.05, but I know I'm going to have to shift one loop to the left. And so my answer ends up being 0.005, or 5 times 10 to the negative 3, 0, 0. And now that's moles. And this is specifically moles of my acid, of my HCl. And that's equal to, I have to do the same thing here. So I'm going to make it, watch how quick I'm going to do this now. I'm going to go 1 to the right to make it 1 times, which means I have to go 1 to the left to make it equal. So then my answer for this is going to be 0.00490 moles. But this one is my base. That's my sodium hydroxide. Okay. Step 2 is they're going to react with each other. Well, which one do I have less of? I have less of the base. So I'm going to subtract 0.0049 on both sides. So this one's going to be 0.0049, because that's my, pretty much my limiting reagent. And this one's minus 0.00490 moles of the base. The base is going to be the one that's going to react. Okay, so when I subtract this, which is basically step 2, I'm getting 0.00500 moles of my HCl. Let's just do it straight here. Minus 0.00490 moles of the base. And when I do this, I'm going to get 0.00010 moles of the acid. That's my excess. So this is what is in excess. Okay. So now we're at step 3. We're almost there. Step 3 is take this number and divide it by your total volume. So I'm going to take my 0.00010 moles of my acid and divide it by my total volume. Well, my total volume is 50 plus 49. Okay, so I know that that's going to be 99, or 0.0990 liters. Okay, because we do have to be in liters again. And so this is my total volume. So you do want to make sure that you're in liters, not milliliters. Okay, and so now I have my new molarity. So let's go ahead and divide this, see what we get. And we're getting 1.0 times 10 to the negative 3, or 0.0010. And this is our new molarity of the HCl. What matters to us is our H. So step 4 is find your pH. So all I'm going to do is pH is equal to the negative log of H plus, which is 1 times 10 to the negative 3. And that makes my pH equal to, and I want 2 sig figs, 3.00. That's kind of crazy, because if you thought the pH, if you were guessing on a multiple choice question, a lot of times people will say, well, it was 49 mils of the base and 50 mils of the acid, so you know it's going to be acidic, right? But it's only 1 mil off, and so people will say, I think the pH is going to be 6. I think the pH is going to be 5. If you come back up to the titration curve, take a look at this. If you're at 49 mils, which is right around here, and we draw an arrow up, take a look. We are right around a pH of 3, okay? So keep that in mind, because a lot of times people are thinking, oh no, my pH is going to be around a 6 or a 7. You really don't hit this area, this region, until you're exactly at 50 mils, okay? Well, let's take a look at a couple of titration curves here again. So if you have a weak acid or a weak base, we know that the titration curve is going to be a little bit different from what we're used to. So we already talked a little bit about this. So it says we've got a 0.1 molar NaOH added to 50 mils of a 0.1 molar acetic acid, and there are 3 major differences between the curves. Okay, so the weak acid solution is going to have a higher initial pH. So we can see here that if it's weak, then it's going to be a little bit higher. So since we're using a weak acid of acetic acid, with a strong base. The pH is going to rise more rapidly at the start, but less rapidly near the equivalence point. So you can see that it kind of like starts off with a little bit of a curve, and then it kind of flattens out a little bit. So it rises more rapidly at the start, but then less rapidly as you approach your equivalence point. And the pH of the equivalence point is going to be greater than 7.00. And we can see here that at the equivalence point, it's closer to something like a 9, okay? So we've got a couple points of emphasis. It says for a strong acid, weak base, or the other way around, the pH is going to change rapidly at the beginning, and then it's going to have a gradual slope until you near the equivalence point. The gradual slope results from a buffer solution that's being produced. So since we are making a buffer solution, why? Why is a buffer solution produced? Well, it's not there in the beginning, but we remember that a buffer is simply a weak acid and its salt, or a weak base and its salt, or its conjugate. So as soon as they start reacting, the weak acid is going to create a buffer once it has its weak salt in there, or the weak base with its salt, okay? So let's take a look real quick. I like this video. It kind of does a nice job of explaining this. So let's take a look at this real quick to understand. And really, I want you to get an idea of what happens at halfway to the equivalence point, because this is a very important point. The AP will stress this. I've seen it year after year, so maybe like or every other year, I'll see a question that may be pertaining to this. But what's the importance of halfway to the equivalence point? What they're talking about when they say halfway to the equivalence point is, if my equivalence point is at 50 mils, then what's happening at like 25? That's what we're talking about here, okay? And so that's kind of an important part.
In this lecture, we're going to talk about titrating an acid using a base. Now, if you don't know what titration is, and you don't know what an equivalence point is, then check out the link below. So once again, we're titrating an acid with a base. And here's our titration curve, where the y-axis is pH, and the x-axis is the volume of base added. Now, we've defined the equivalence point to be the point at which all the acid has been neutralized. So every single molecule of acid in our buffer system has been neutralized. Now we can also define something called the half equivalence point. And the half equivalence point is the point at which exactly half of the acid in our buffer system has been neutralized. Now suppose we choose our buffer system to consist of acetic acid. Now acetic acid associates into acetate ion and an H plus ion. Now suppose we begin adding some volume of our base, and suppose we choose our base to be ammonia. So we're adding the volume of ammonia into our acetic acid. Now the reaction looks like this. The conjugate acid, acetic acid, dissociates into the conjugate base, acetate ion. This base, the ammonia, gains an H, becoming ammonia. Now, so let's look at this definition again. The half equivalence point is the point at which exactly half of the acid, exactly half of this guy, has dissociated into this guy, aka has been neutralized. So that means we can define the half equivalence point in another way. The half equivalence point is the point at which the concentration of the conjugate acid equals the concentration of the conjugate base, because half of this is now this. So the concentration of this guy equals this guy. Well, why is this definition important? Well, we'll see why in a second. Let's look at the Henderson-Hasselbark formula or equation. Now, if you don't know what this formula is, check out the link above. So, this equation states that pH is equal to pKa of our acid plus log of this ratio, the concentration of the conjugate base over the concentration of the conjugate acid. And this pH is the pH of our buffer system. So, notice that since this guy equals this guy, this divided by this is 1. So, what's inside here is simply 1. So let's rewrite it. pH is equal to pKa plus log of 1. But what's log of 1? Well, log of 1 is 0, and that means pH equals pKa. Well, that's nice and all, but why is that important? Where is the significance? Well, this means that now we can choose the pH of our buffer system by simply choosing an acid with pKa that's closest to our desired pH. So suppose, for example, I want my buffer system to have a pH of 4.7. Now, how I find the acid to use is I simply find the acid with the pKa value closest to 4.7. Now, I go online, I find my table, I look up an acid with a pH or a pKa closest to a pH of 4.7, and I find that it's acetic acid. So now I know, using this equation here, that if I choose my buffer system to consist of acetic acid, my pH of my buffer system will be 4.7, and that's important.
Okay, so I just want to take a look back over here and just kind of remind you a little bit of what he's talking about. So let's see if I can just kind of move this over. Okay, so just to kind of reiterate this, because this is really important. So the most important thing is, once your acid is equal to your conjugate base, so in other words, CB over A are equal to each other, we know that we're going to get log of 1, which is going to be equal to 0. And if your pH and your pKa are equal to each other, this is a very common question. What they'll do is they'll give you a list of pKa values with different indicators. And so they'll say, which one do you want to use? And so you want to choose the one that's going to hit at wherever your equivalence point is going to be. That's the indicator that you're going to want to use. And so again, if they give you the pKa, you want to use the one that matches that particular pH of what you're looking for, okay? So we can kind of go in two different ways. All right, so let's come back here. And so again, the half equivalence point is the volume where the pH equals pKa because your acid and your conjugate base concentrations are the same. Okay, and then this is just going to do the same thing except for now we have hydrochloric acid, which is a strong acid, with ammonia, NH3, or ammonium hydroxide, which is a weak base. And so what are the differences here? Now we're going to see that our pH actually starts a little bit lower than what it should have if it was strong. So a lower initial pH. The pH is going to drop more rapidly again. You can see that little drop there, and then it's going to be more steady. So more rapidly at the start, but then less rapidly near the equivalence point. And then now we can see that our pH at our equivalence point is going to be lower. So if you have a weak base, your pH should be lower, it should be more acidic. If you have a weak acid, then it should be a little bit higher or more basic at the equivalence point. Okay. And again, the halfway to the equivalence point, we know is where we've got a situation where our concentration of our conjugate base, or our whichever one that it is that we're doing here. In this case, it's going to be a base. So it's going to be the conjugate acid is equal to our base, okay, at that point there. Okay. Titrations involving polyprotic acids. So when you have a polyprotic, that means that you have more than one hydrogen ion. Remember, the bases are going to dissociate right away. So if you have a hydroxide and you have two hydroxides, they're just going to come off right at the same time. But if it's an acid, for example, we've got something like carbonic acid. Now, it is a weak acid anyway, okay? But what's going to happen first is the H2CO3 is actually going to break up and form HCl3 minus first. Then your HCl3 minus is going to give off another hydrogen ion to form Cl3 minus. So it happens in two steps. And when that happens then, we actually get two equivalence points, okay? And this one, what we're seeing is they've got an H3A. So for example, let's imagine that it's phosphoric acid. And so what's going to happen is you're going to get 3 points of inflection. So we're going to see the first one come off, the second one come off, and then the third one come off, okay? And so that would be what we would call a triprotic acid, okay? The last thing that I want, just very briefly here, I want to talk to you about choosing indicators. There are so many different indicators. And you can see here that it'll give you like the pKa value of like thymol blue is at like a 9.2 and what color it changes. Or like, for example, it'll say bromophenol blue is at a 4.1, yellow to blue, and what happens? So there are a whole bunch of different indicators and where they change colors, okay? And so the question is, how do we figure out what indicator to use depending on what our titration is, okay? And so I'm going to tell you that the biggest idea is you do not want to, you want to hit it where your equivalence point and your indicator are changing around the same time, okay? So phenolphthalein tends to be a very popular one. And so what ends up happening is, depending on whether it has the hydrogen added in or the hydrogen off of it, it can be a different color. So we know it's clear. In acidic solutions, it's actually clear. And then once it loses that hydrogen ion and becomes more basic, then it actually turns into a pink color. And what's happening is, the way that I always think about it is, your acid and your base want to react with each other, okay? But once there's no more acid to react with the base, then your base is going to actually react with the indicator. And so that's going to get it to change colors, okay? And so again, we know that there's a big range. And so a lot of times what they'll do is that, like I was saying before, they're going to give you the pK value, okay, of the indicator. And so they'll say like litmus is a 6.5, methyl orange is a 3.7, phenolphthalein is like a 9.3. Okay, so what ends up happening is they're going to give us a range, okay, because it's not going to be an exact amount. And so we can see that, like, for example, phenolphthalein is between 8.3 and 10, okay? So let's take a look down here and see what happens. So this is going to be a strong acid, strong base. Phenolphthalein is typically going to be very popular. You're going to see why in just a second, but we've got methyl orange and then we have phenolphthalein. Notice that with our strong acid, strong base, we've got such a big region here where our color change is going to be obvious at the equivalence point. So whether your equivalence point is happening at 7, or if it's happening here, if it's happening here, we're still in the safe zone, okay? And so phenolphthalein tends to be very popular for something like that. So it says, you can see that neither indicator changes color at the equivalence point. However, the graph is so steep that there's no difference in that volume in which indicator you end up choosing when they're both strong, okay? So let's take a look at a strong acid versus a weak base. Well, if you do this, you're going to see that phenolphthalein is actually out of that range. We want it where the equivalence point is going to hit. And so you can see here that methyl orange actually does hit in that range of where your point is where it's steep, okay? And so that's kind of what you're looking for in something like this. Now we've got a weak acid and a strong base. Well, now since I have a strong base, I know that my pH should be higher at the equivalence point. So now phenolphthalein is going to be appropriate, but methyl orange is not going to be an appropriate indicator, okay? So just to kind of give you an idea of like, how are you supposed to choose which one it is? And then if they give you a chart with pK values, that's how you would end up choosing that, all right? And that's all I have for you for titrations. Happy day, everybody.